Good morning. I'm Devasena. In this lecture, we are going to discuss about second order systems time response analysis subjected to unit step input under damped condition. This topic is present in the subject control systems. Time response analysis of second order system. Consider a second order system shown below. Here is a representation of a second order system. The value of g of s for this second order system is omega n square divided by s into s plus 2 zeta omega n. A unity feedback is applied to this circuit. A negative feedback is applied. The input is R of signal, R of s, and the output is C of s. The closed loop transfer function is given by the ratio of Laplace transform of output variable to the input variable, that is equal to g of s divided by 1 plus g of s. In this diagram, we have considered that the unity feedback is applied. Therefore, the value of h of s is equal to 0. So, the formula for calculating c of s by r of s becomes g of s divided by 1 plus g of s. If you substitute the value of g of s is equal to omega n square divided by s into s plus 2 zeta omega n in this equation, means we get c of s by r of s is equal to omega n square divided by s into s plus 2 zeta omega n. This is our numerator term, the whole divided by 1 plus omega n square divided by s into s plus 2 zeta omega n. I have considered this as equation 1. That is, simplifying equation 1 means we get c of s by r of s is equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square. I have considered this as equation 2, where zeta is called the damping ratio, omega n is called undamped natural frequency, zeta is equal to actual damping divided by initial damping. The denominator polynomial of a closed loop transfer function is known as characteristic polynomial, and when equated to 0, it is called as characteristic equation. The characteristic equation for the second order system is s square plus 2 zeta omega ns plus omega n square, that is equal to 0. S square plus 2 zeta omega ns plus omega n square, that is equal to 0. Consider this as equation 3. The roots of the equation are, the equation 3 is a quadratic equation, so we can represent the roots of the quadratic equation with the help of the formula minus b plus or minus square root of b square minus 4ac divided by 2a. So roots are s1 comma s2 is equal to minus 2 zeta omega n plus or minus square root of 4 zeta square omega n square minus 4 omega n square divided by 2. Consider this as equation 4. Simplifying the above equation, we get s1 comma s2 is equal to minus zeta omega n plus or minus omega n square root of zeta square minus 1. Consider this as equation 5. Here is a representation of a critically damped system, underdamped system, overdamped system for a step input. Case 1, for zeta is less than 1, the system is termed as underdamped system. Therefore, the roots are complex for the underdamped system. The roots are represented as s1 comma s2 is equal to minus zeta omega n plus or minus j omega n square root of 1 minus zeta square. Let us define sigma is equal to zeta omega n, and the damping factor is equal to 1 by t. Therefore, omega d is the omega n square root of 1 minus zeta square. So, the roots are s1 comma s2 is equal to minus sigma plus or minus j omega d. Case 2, zeta is equal to 1. The system is termed to be critically damped system. Therefore, the roots are real and equal for critically damped system. Here is the value of the roots. S1, S2 is equal to minus omega n. Case 3, when the damping ratio zeta is greater than 1 means the system is termed to be overdamped system. The roots are real and unequal for the overdamped system. The value of the roots are S1, S2 is equal to minus zeta omega n plus or minus omega n square root of zeta square minus 1. Case 4, zeta is equal to 0. The system is termed to be undamped system or oscillating system. The roots are complex conjugates for the undamped system. Here is the value of the roots. S1, S2 is equal to plus or minus j omega n for undamped system. Generally, real parts of roots of characteristic equation contribute damping to the system, and imaginary part of the characteristic equation contribute oscillations to the system. Time response analysis of second order system to a unit step input. Assume underdamped system, that is the value of zeta is less than 1. Consider a second order system with the closed loop transfer function as C of s by R of s is equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. This is considered to be equation 1. The value of C of s is equal to omega n square into R of s divided by s square plus 2 zeta omega ns plus omega n square. Consider this is equation 2. For unit step input, the value of R of s is equal to 1 by s. So, C of s value is equal to omega n square divided by s into s square plus 2 zeta omega ns plus omega n square. Consider this as equation 3. In the equation 3, we have substituted the value of R of s as 1 by s. Using partial fraction method, we have omega n square divided by s into s square plus 2 zeta omega ns plus omega n square can be represented as a divided by s plus bs plus c the whole divided by s square plus 2 zeta omega ns plus omega n square. Consider this as equation 4, that is omega n square is equal to a into s square plus 2 zeta omega ns plus omega n square plus bs plus c into s. That is omega n square is equal to a square plus 2a zeta omega ns plus a omega n square plus b square plus cs. So omega n square is equal to s square into a plus b plus 2a zeta omega n plus c into s plus a omega n square. Consider this as equation 5. Omega n square is equal to s square open bracket a plus b close bracket plus 2a zeta omega n plus a close bracket into s plus a omega n square. Equating the coefficients of s square term, s term and the constant term, we get, now we are equating the coefficients of s square term, that is a plus b is equal to 0. Equating the coefficients of s term means we get 2 zeta omega n a plus c is equal to 0. Now equating the constant term, we get a omega n square is equal to omega n square. Solving the values for a, b and c, we get the value of a is equal to 1, the value of b is equal to minus 1 and the value of c is equal to minus 2 zeta omega n. Put the values of a is equal to 1 and b is equal to minus 1 and c is equal to minus 2 zeta omega n in equation 4 means the value of equation 4 becomes C of s is equal to omega n square divided by s into s square plus 2 zeta omega ns plus omega n square, that is equal to a by s plus bs plus c divided by s square plus 2 zeta omega ns plus omega n square. That is C of s is equal to 1 by s plus minus 1 into s plus minus 2 zeta omega n the whole divided by s square plus 2 zeta omega n s plus omega n square. This can be represented as 1 by s minus s plus 2 zeta omega n divided by s square plus 2 zeta omega n s plus omega n square. Consider this as equation 6. Adding and subtracting zeta square omega n square in the denominator of second function of equation 6, we get C of s is equal to 1 by s minus s plus 2 zeta omega n divided by s square plus 2 zeta omega n s plus omega n square plus zeta square omega n square minus zeta square omega n square. Consider this as equation 7. That is C of s is equal to 1 by s minus, in the numerator we have split 2 zeta omega n as zeta omega n and zeta omega n. So we get s plus zeta omega n plus zeta omega n the whole divided by, we have combined the term that is present in the denominator. So we get s plus zeta omega n the whole square plus omega n square into 1 minus zeta square. Consider this as equation 8. As per the definition of omega d for underdamped system, we get omega d square is equal to omega n square into 1 minus zeta square, because we have defined the value of omega d is equal to omega n into square root of 1 minus zeta square. So we have taken the square of omega t, that is omega t square is equal to omega n square into 1 minus zeta square. So we have C of s is equal to 1 divided by s minus s plus zeta omega n plus zeta omega n the whole divided by s plus zeta omega n square plus omega t square. That is C of s is equal to 1 by s minus s plus zeta omega n divided by s plus zeta omega n the whole square plus omega t square minus zeta omega n divided by s plus zeta omega n square plus omega t square. Consider this as equation 9. Taking inverse Laplace transform of equation 9, we get Laplace inverse of C of s is C of t, and the Laplace inverse of 1 by s is 1. Laplace inverse of s plus zeta omega n divided by s plus zeta omega n square plus omega t square value is e power minus zeta omega n t cos omega dt, and Laplace inverse of zeta omega n divided by s square s plus zeta omega n the whole square plus omega t square value is e power minus zeta omega n d sin omega dt. So the Laplace inverse of equation 9 is C of t is equal to 1 minus e power minus zeta omega n t cos omega dt plus zeta omega n divided by omega d e power minus zeta omega n t sin omega dt. Consider this as equation 10. So C of t is equal to 1 minus, we have taken e power minus zeta omega n t as common. So e power minus zeta omega n t open bracket cos omega dt plus zeta omega n divided by omega n square root of 1 minus zeta square sin omega dt. Here we have expanded the value of omega d as omega n square root of 1 minus zeta square. This we already considered. Omega d is equal to omega n square root of 1 minus zeta square. So I have substituted that value here. That is C of t is equal to 1 minus e power minus zeta omega n t divided by square root of 1 minus zeta square open bracket square root of 1 minus zeta square cos omega dt plus zeta sin omega dt. I have considered this as equation 12. Consider the triangle shown below. Here is the triangle, trigonometrical triangle, because we have to simplify the equation 12 with the help of the formula, trigonometrical formula. From the triangle, the value of sin phi is equal to square root of 1 minus zeta square. That is the sin phi value is opposite side. Opposite side of theta is square root of 1 minus zeta square. And the value of cos phi is zeta, adjacent side. And Sin phi by cos phi is equal to square root of 1 minus zeta square by zeta. That is tan phi is equal to square root of 1 minus zeta square by theta, or theta phi is equal to tan inverse of square root of 1 minus zeta square divided by zeta. Put these values in equation 12. We get equation 12 becomes C of t is equal to 1 minus e power minus zeta omega nt divided by square root of 1 minus zeta square, open bracket, sin phi cos omega dt plus cos phi sin omega dt, close the bracket. Consider this as equation 3 because we have substituted the values of sin phi and cos phi in equation 12. By trigonometry, we know that sin of a plus b is equal to sin a cos b plus cos a sin b. With the help of this formula, we are going to simplify the above equation 13. So the equation 13 becomes C of t is equal to 1 minus e power minus zeta omega nt divided by square root of 1 minus zeta square sin of phi plus omega dt. Consider this as equation 14, where phi is equal to tan inverse of square root of 1 minus zeta square divided by zeta. An underdamped system is most preferable for all systems. The reason being that when it is disturbed by external signals, then it comes back to steady state quickly. The steady state error E suffix ss is given by E suffix ss is equal to limit t tends to infinity, open bracket, r of t minus c of t. For the unit step input, the value of r of t is 1 and we have obtained the value of c of t. So substitute the value of r of t and c of t means the steady state error becomes E suffix ss is equal to limit t tends to infinity, open bracket, 1 minus, open bracket, 1 minus e power minus zeta omega nt divided by square root of 1 minus zeta square sin of phi plus omega dt, close brackets. That is E suffix ss is equal to 1 minus 0. So the value of ESS is equal to 0. The time constant t is equal to 1 by sigma, that is equal to 1 divided by zeta omega n. Since E suffix ss is equal to 0, the second order system is capable of responding to a unit step input without any steady state error. The response is exponentially decaying sinusoidal wave for underdamped system. The decay depends on the time constant. For larger values of t is equal to 1 divided by zeta omega n, the exponential decay delay will be faster. Thank you very much for listening this lecture. For further updates, kindly subscribe this channel. If you like this video means kindly share this video to your friends. Thank you.